So for the first learning task, these are the questions that I will be answering. For problem set number 1, I will be answering question 4-19, and for problem set number 2, I will be answering question 9-7. So for problem set number 1, question 4-19, we are tasked to calculate the P functions for each ion in a solution that is first 0.300 molar in sodium bromide. So the way I approach this question is first I tabulate the reaction to know the ratio of the concentrations of the products and the reactants. Then after knowing their concentrations, I can now solve for their P functions. So for this first item, we could see that the ratio between the two ions in the products is 1:1 ratio with the sodium bromide, which is why they all have equal concentrations of 0.0300 molar. Since the sodium ion and the bromide ion have equal concentration, they also have equal P functions. So we could just solve it by negative logarithm of 0.0300, which is 1.523. For the next item, we have 0.0200 molar in barium bromide. So based on the table, we could see that the ratio between the barium ion and the bromide ion is 1:2, meaning that bromide ions are twice the number or the amount of the barium ions, while the barium ions have a 1:1 ratio with the barium bromide, which means that they have the same concentration of 0.0200 molar. And since the bromide ions is twice of that, bromide ions have a concentration of 0.0400 molar. Since we have the concentration of the ions now, we can solve for their P functions. For the barium ions, we have the negative log of 0.200 m, which is 1.699. And for the P function for the bromide ions, we have the negative log 0.0400, which is 1.398. So for the next item, we have 5.5 times 10 raised to negative 3 molar in barium hydroxide. Once again, we can see that the ratio between the products is 1:2. And the ratio between the barium ions is 1:1 with the barium hydroxide, which means that it has the same concentration of 5.5 times 10 to the negative 3 molar. And since the hydroxide ions is twice of that, it has a concentration of 11 times 10 raised to negative 3 molar. To compute for their P functions, the P function for the barium ions is the negative log of 5.5 times 10 raised to negative 3, which is 2.26, while the P function for the hydroxide ions is negative log of 11 times 10 raised to negative 3, which is 1.96. For the next problem, we have two compounds in one solution, HCl and NaCl, with different concentrations. So first, I solve the concentrations of the ions in HCl. We can see that the ratio between the hydrogen ions and the chloride ions to be 1:1, which is also 1:1 with the ratio of the hydrogen chloride, which means all of them have a same concentration of 0.020 molar. The same goes for the sodium chloride, which has a 1:1 ratio between the products and the reactants, which means all of them have a concentration of 0.10 molar. Since both of them have chloride ions, we need to get the sum of their concentrations. So we have 0.20 molar of chlorides in the first plus 0.10 molar in the sodium chloride to have 0.030 molar of total chloride concentration. Now that we have their concentrations, we can solve for their P functions. For the pH, we have the negative log of 0.20, which is 1.7. For the sodium ions, we have the negative log of 0.010 molar, which is 2. And lastly, for the P function of the chloride ions, we have the negative log of 0.030, which is 1.52. So this next item, 8.7 times 10 raised to negative 3 molar in CaCl2, and 6.6 times 10 raised to negative 3 molar in barium chloride. It follows the same principle as the previous item, wherein there are two compounds in the solution. So first, I solve for the concentrations in the calcium chloride. So as we can see, the calcium ions is 1:1 with the calcium chloride, which is why it has the same concentration of 8.7 times 10 raised to negative 3 molar. And twice of that is the chloride ions, which is 17.4 times 10 raised to negative 3 molar. On the other hand, it is also the same for the barium chloride, wherein the barium ions is 1:1 with the barium chloride, which is why it has the same concentration of 6.6 times 10 raised to negative 3 molar. And twice of that is the chloride ions as well, which is 13.2 times 10 raised to negative 3 molar. Just like in the previous problem, we added the concentrations of the chloride ions, which amounted to 30.6 times 10 raised to negative 3 molar. Now that we have their concentrations, we can solve for their P functions. For the calcium ions, we have the negative log of 8.7 times 10 raised to negative 3, which is 2.06. For the barium ions, we have negative log of 6.6 times 10 raised to negative 3, which is 2.18. Lastly, for the P function of the chloride ions, we have the negative log of 30.6 times 10 raised to negative 3, which is 1.51. And for the last item for this question, we have 2.8 times 10 raised to negative 8 molar in zinc nitrate and 6.6 times 10 raised to negative 7 molar in cadmium nitrate. Just like in the previous two problems, first I computed for the concentrations of the first compound. So as we can see, the concentration of the zinc ions is 1:1 with the zinc nitrate, which is why it has the same concentration of 2.8 times 10 raised to negative 8 molar. And twice of that is the nitrate ions, which is 5.6 times 10 raised to negative 8 molar. The same goes for the cadmium nitrate, wherein the cadmium ions is 1:1 ratio with the cadmium nitrate, which is why it has the same concentration of 6.6 times 10 raised to negative 7 molar. And twice of that again is the nitrate ions, which is 13.2 times 10 raised to negative 7. Again, we added the concentrations of the two nitrates concentrations, which is 1.376 times 10 raised to negative 6 molar. Now that we have the concentration of the ions, we can compute for their P functions. For the zinc ions, it is the negative log of the 2.8 times 10 raised to negative 8, which is 7.55. The P function for the cadmium ions, we have the negative log of 6.6 times 10 raised to negative 7, which is 6.18. And lastly, for the P function of the nitrate ions, we have the negative log of 1.376 times 10 raised to negative 6, which is 5.86. So now for problem set number 2, question 9-7, we are tasked to write the equilibrium constant expressions and obtain numerical values for each constant in. So before I get into that, here is the table that I will be using as a reference for the Ka values for the acid dissociation constants. For the first item, we have the basic dissociation of aniline C6H5NH2. So here's the equilibrium equation: C6H5NH2 aqueous plus water, we get hydroxide ions, and C6H5NH3 ions. In equilibrium constant expressions, we do not consider liquid water or liquid H2O, which is why we are only considering the aqueous parts of the equation. And in equilibrium constant expressions, we take the quotient of the product of the products and the products of the reactants, which is why for the equilibrium constant expression, we have the product of the concentration of the OH ions and the C6H5NH3 ions divided by the concentration of the C6H5NH2. In the table, we are only given the Ka values. However, we can solve for the Kb values by this equation, Kw over Ka. Kw is the constant for water, which is 1.0 times 10 raised to negative 4. And our Ka for the aniline ion, we have 2.51 times 10 raised to negative 5. So the Kb for the basic dissociation of aniline is 4.0 times 10 raised to negative 10. Next, we have the acidic dissociation of hypochlorous acid, HClO. So here is the equilibrium equation. Once again, we only take into account the aqueous parts of the equation, which is why we have the equilibrium constant equation. Ka is equal to concentration of chloride ions times concentration of hydroxide ions all over the concentration of hypochlorous acid concentration. Since this is acidic dissociation, we could just take the value of Ka given in the table, which is 3.0 times 10 raised to negative 8. For the next item, we have the acidic dissociation of methyl ammonium hydrochloride. Since this is acidic dissociation, we will just again refer the Ka value from the table. But first, here's the equilibrium equation. Ka will be CH3NH2 times HCl, since they are the products, all over the CH3NH3Cl, which is the reactant. Once again, its Ka value in the table is 2.3 times 10 raised to negative 11. So for the next item, we have the basic dissociation of sodium nitrite. Sodium nitrite plus water, we have sodium hydroxide and nitrous acid. So for the Kb, we have the product, the concentration of the NaOH times the concentration of the HNO2 all over the concentration of the reactants NaNO2. Once again, this is a basic dissociation. That is why we need to solve for Kb. And given the Ka of 7.1 times 10 raised to negative 4, we could just divide it from the Kw of 1.0 times 10 raised to negative 14 to get 1.4 times 10 raised to negative 11. For the next item, we have the dissociation of the arsenic acid to hydroxide ions and arsenate ions. It was not indicated if it is acidic or basic. However, we have hydronium ions in the product, which indicate that this is an acidic dissociation. Since the arsenic acid is a polyprotic acid, which means that it can dissociate in more than one times, we have multiple equilibrium equations. Since from arsenic acid to the arsenate, we have a loss of 3 hydrogen ions, we have 3 equilibrium equations. First, we have the H3ASO4 plus water dissociates into hydronium ions and H2ASO4 minus, and that will be dissociated again when dissolved into water, which becomes hydronium ions and HAASO4 2 minus, which then dissociates again when dissolved in water, which produces hydronium ions, and finally the arsenate ions that we need. Since we had 3 equilibrium equations, we need to have 3 equilibrium constant expressions, and since this is an acidic dissociation, we could just refer to the table for their values, and all of their values are taken into account in the table, which is here, which is why the first Ka is in the first equilibrium equation, which is between the H2ASO4 and the hydronium ions in the product, and the H3ASO4 in the reactant, which yields 5.8 times 10 raised to negative 3. The next Ka is 1.1 times 10 raised to negative 7, and the Ka of the next and last dissociation is 3.7 times 10 raised to negative 12. However, this is not yet the final answer, for we need to take the total acid dissociation constant of the reactions, which is obtained just by multiplying the 3 Kas that we got. So multiplying the 3, we get 2.0 times 10 raised to negative 21 as our final acid dissociation constant. So now for the final item for question 9-7, we have the reaction of oxalate ions with water to give oxalic acid and hydroxide ions. So just like in the previous item, we have multiple equilibrium equations. First, we have the oxalate ions plus water to give Hc2O4 minus plus OH minus, and then the Hc2O4 minus reacts again with water to yield the oxalic acid and the hydroxide ions. So since again we have two equilibrium equations, we have two equilibrium constant expressions. First is for the formation of the Hc2O4 minus, and then the next is for the formation of the oxalic acid. Since this is a basic dissociation because of the formation of the hydroxide ions, we need to solve first for the Kb. Again, in the table, the first and second dissociation for the oxalic acid is already given, which is 5.6 times 10 raised to negative 2 and 5.4 times 10 raised to negative 5. We only need to solve for the Kb from them. So the Kb for the first reaction, we have 1.8 times 10 raised to negative 10, and for the second Kb, we have 1.8 times 10 raised to negative 13. Once again, to solve for the total Kb, we just need to multiply Kb1 and Kb2. So now we have a total basic dissociation constant of 3.2 times 10 raised to negative 23. That is all. Thank you.